it is an interesting, the first question actually is very interesting. Sorry. So we are doing, so okay, I have not presented the screen. One second. All right. So INMO 2023. Okay. I mean, and just to tell you, the official solutions are out. Okay. So, you can look at them after you try it enough and you can see what you can, but obviously let's, yeah, do the problems first. So this is problem number one. Okay. Problem number one is the following. So you have a set S. Okay. So S is a set. Okay. Such that, so S is maybe just a subset of natural. Is it a finite set? Yeah, it's finite. Yeah, this is a subset of natural numbers, and just using a fancy notation, finite set. Okay, there are 23 ordered pairs. Okay, there are 23 ordered pairs x comma y, such that xy is a perfect square. I will hope that you people have at least seen the question, so it's not completely new. Okay, is a perfect square. Okay. This is all, and then it's a very elegant question. Okay, show that there exists, and this is a very different reason I think for this, for which this happens, than just pigeonhole principle, something like that. There are at least 4, yeah, from S. Okay, at least 4 elements from S. Okay, uh, such that, let's say 4 elements X, Y, so I'll use A, B, C, D, such that none of the pairwise products, none of the pairwise products, okay, is a perfect square. So is this question clear? The language, right? This is, yes, yeah. So AB will not be perfect square, AC will not be perfect square, AD will not be, yeah. All the 4 choose 2, none of them are perfect squares. Yeah. So really here, like what I was initially thinking is maybe you try to um, somehow create pigeonholes, so that two things which don't form a perfect square go to the same hole. Okay, and then we somehow show that at least one hole contains 4 things, but that doesn't seem to work. It is sort of the opposite, right? Don't form a perfect square, right? So it is sort of the opposite. So we have to show that there are at least 4 pigeonholes, things like something like that, right? There are at least 4 boxes. So how are we going to create our boxes? Okay. So that's the way I am just putting it. So this will mostly be a little instructive to begin with because I've thought about this little bit. Okay. So how to make boxes? So we are going to take S and we are going to put the elements of S into boxes. Okay, and the idea would be that the two things in different boxes would actually not, two things are in different boxes means that the product is not a perfect square. Okay, something like that. Okay, so we will show that there are enough. So to put this mathematically, we are going to partition. So what you're going to learn here, the way to create this, uh, you know, the way to break up a set. Okay, what you're going to learn here is will be extremely fundamental. It's a fundamental idea which we'll keep using. Is that we are going to partition S. Okay, so that elements in the in same part, uh, their pairwise product is perfect square. Okay, so that is how we will try. Okay, so let us see. So if we start with an element A, okay, and we put it in a box. Now, if A times B is a perfect square, then I will put B in the same box. Okay, right? So in this way, I want to say that you will get a partition of the set. Okay, partition means that they'll break up into disjoint things. The disjointness is really the hard thing here. Okay, so rather than saying that I will put A and B in the same part if AB is a perfect square, let me say it in a more mathematical way. I'll define an equivalence relation. Okay, I will say sorry, I will say that X is equivalent to Y if XY is a perfect square. Equivalence relations you have done, right? Binary relations. Yeah, Ishana, binary relations. No. Okay, okay. So here is what you do, right? So you may have seen this. So you take a set S, right? And what is a binary relation on that? You take S cross S and you take a subset of this. Right, so you take pairs, right? And binary relation, so reflexive relation where T is a reflexive relation. So why is T called a relation? Because the pairs that T contains, basically it's saying that those two pairs are related, right? And then what is a reflexive relation? If A comma A is there in T for every A in S. Reflexive relation, no? I've not heard that term before. No, okay. So NCRT doesn't have all that. Oh, maybe it's in class 11. Okay, no problem, no problem. So then we will not say that. Then we will not use the word term. Otherwise, you will have a problem. I will introduce that later, but we should do the try to solve the problem first. Okay, no issues. That's not a problem, but you will see it's a useful language. But so I will come back to the idea. The idea is that I have A, and then I will put some B in it if AB is a perfect square. Okay. So let's look at this. So you take A and then you look at you look at SA. Okay. I think in fact that's how they do it in the solution because they don't want to. But for mathematicians, like the way we do a little bit, I'm not a mathematician, but like in the process maybe, but we think of it directly in a natural way. But obviously that takes some training to think of that naturally, but then you can do it like this. You take SA and you just formalize your idea, which is you put all B, but maybe let's not use BX, yeah, because X, AX, such that AX is a perfect square. This is fine. How I'm taking SA, right? This is what you want to do, right? You want to collect the things which form a perfect square. And now you tell, so now similarly you can form PX. What do you want to prove about these two things? No, I mean, you will, I'm sorry. Yeah. No, this is not what I wanted to say. Okay. And you take those y such that by is perfect square. Right. You will take those things such that the product is a perfect square. You want to put them in one box. So what do we want to prove? We want to prove that SA and SB are disjoint. Then only it will form a partition, right? You have A and you have B, and then you look at all those things which form a perfect square with B, and then you look at all those things which form a perfect square with A. Okay, these two things we want to them to be disjoint, so that in that way we can get a partition. Okay, then we will say that this partition has at least 4 parts. Then we will think about that. Then through that we will get the 4 things. But first you want them to be disjoint. Can you prove that they are disjoint? Okay, let us think about that. So either they will be disjoint or they can be same. Yeah. Yes. Yeah. So let's take that case. If AB is a perfect square, is some k square, that implies that B is in SA. Then let's see, if BY is a perfect square, then Y cannot be equal to A. Yeah, that's fine. Okay, if you take M to be different, but I want to say that then A times Y will be a perfect square. Yeah, can we say such things? Can we say that A times Y is a perfect square? This is what you want to say, right? That way you'll bring the SB inside SA. Right, so anything Y which is in SB, I want to say that it's in SA also. So can you show that this is also a perfect square? But this should not be difficult, I think. This is a perfect square because it's an integer and it's a ratio of two perfect squares. Right, this is all because I know what I want to do. That's why it seems easy for me, and maybe it's a little difficult for you, but it will not be once you understand that you want to get a partition. Ishana, is it okay? Right, so what have we proved? We have proved that SB is in SA. I mean, if B is in A, right? So what Nagesh started with, like if B is in A, okay, then that implies that SB is in SA. But then you understand, right? B is in A means A is in B. And so then SB equal to SA. Okay. And otherwise they are disjoint. That also you can prove. Okay. So if B is not in A, you can prove they are disjoint. So I'm leaving that to you. All right, I'm leaving that. Okay. So this is something which you can check. But please note this down and try to, from this definition, try to prove that either SA and SB are equal or they are disjoint. Okay. All right. So we have basically shown that. So what have we shown? Okay. Now you look at this. Now you look at SA only. Okay. So we have shown that these things partition thing. Hmm. So now this is SA is x such that AX is a perfect square. Okay. But you see the feature of SA, right? That any two things in SA will form a perfect square. I mean, that is how it should be, right? Right? Any two things in it will form a perfect square. Let's say that x1 and x2 are in SA. You want to show this is a perfect square, but this is just, right? I mean, you knew you wanted to show this because that's what this that was the spirit, that two things that form a perfect square we want to put them in one block. But for the sake of definition, we said like this, with reference to one element. Okay. All right. So what have we done? Right. So we have partitioned the set. Okay. So I'll just write this here. All this will seem much more natural with the language of equivalence relations, partitions, and so on, which I have not formally covered because it's a bit mathematical, like it's a little, yeah, mature kind of thing. But that is the correct thing. So you see, the first time I saw this question, first few minutes I was thinking pajama principle. Next few minutes I was like, okay, some equivalence relation. Put the equivalence relation. Two things which form a perfect square, put them in equivalence relation. Okay? Define a relation like that, and you would expect it to be equivalence, and it is equivalence, and then the game goes on. Okay, so you catch the correct way to do the problem in that, with that language, because possibly the people making this question are also thinking like that. Actually, that's one way to succeed at Olympiad questions. Because usually you don't know if there is some theory, general theory behind. There may be, but that theory may be too far ahead for. So anyway, let's. So what have we done? Yeah. So we have partitioned S into uh, partitioned S. Just saying that. Okay. Each part. Okay. Rather elements, or maybe I'll say like this. Yeah. Two elements are in same part if their product is perfect square. Do you agree? Yeah. Obviously, you have to still write a proof that two elements are in the same part. Then you show then that part we have proved, and the other side we have proved it. But you know it's correct. So now we need to. What do we need to show now? What does this mean? It means that two things are in different parts. Yeah. It means that their product is not a perfect square. And that is if and only if also, because that's just the complement of this if and only if. But simply put, that's also true. So what do you want to show? That there are at least four parts. Right. You want to show that there are at least four parts. So the whole problem comes down to this elegant, that's all. Right. So we just want to show that there are at least 4 parts. We have understood the parts. We have left some mathematical checking, but we have understood what the parts mean. I want to just show that there are at least 4 parts. Now, so far it was just pure mathematics. Now some numbers will come, like some optimization will come related with this. So let's say that there is parts are P1, P2. Then what do you know? You know that the size of the parts, what do you know? I'm just saying cardinality of that subset. That's the size of the part, right? And so on. It's a finite sum, but that's equal to 2023. Anything more we can say about the parts? Oh no, sorry. This is not 2023. Absolutely wrong. It is a size of S which is not given. Sorry. Yeah. So what will 2023 be in terms of the parts? Okay. So let's say that this is part 1. You will see that all this is very simple maths. It's only that we have not done it. But yeah, if you look at the part P1, say that part is P1, then what contribution does it make to this 2023, this ordered pairs? P1 square, yes, because have they said distinct? No, they have not said that X and Y have to be distinct, right? They have not said that, so it's just P1 square. So that's what Nagesh is saying, correct. And then we have this, so now it's the correct thing. Now it's a more useful thing. Its problem is subtle in some way, because you will see, because I know it, so I'm saying it. So, so on. I mean, we don't know how many parts are there. So this is 2023. Now it comes to number theory. Okay, because see, I mean, why I'm saying this, because I mean, why this can be 2023, right? But you want to show that the number of parts is at least 4. Okay, so you want to show that at least 4. Now, how do you show that something is at least 4? You have no idea whether it should be 5 or 6. You cannot. So you have to show that it cannot be 1, 2, or 3, something like that, right? So can you show that it is not 1? Can there be only one part? No, that's impossible, right? That is to be a square then. This is impossible. Can there be 2 parts? Then it will be like this. Is this possible? Check modulo 4, remainders with 4. It's not possible. Sum of 2 squares is either 0 mod 4 or 2 mod 4 or 1 mod 4. Cannot be 3 mod 4. Right? Is that something that's fine? I'm going a bit fast, but like you would, when you see two squares and a number, whether it's possible or not, it's not a big matter. You should be able to do it. You have to just sit down and you have to, okay, this p1 square mod, nothing is just a square. And that p2 square mod, it is just some b square or x square, y square. And then I'm looking to solve this. And sooner or later, you'll be able to conclude, you want to show that you cannot solve it, right? And sooner or later, you'll conclude that you cannot solve it. And then three squares also, it is not possible, but that's your homework. And that will be the problem solution in the end, right? But that's a very small thing, so I will leave it to you. I mean, it's not completely trivial, but it is just some number theory. Okay. Maybe with that, we will just do some more modular arithmetic type number theory, okay? Which we have not done. We have done more of factorization we are focusing on. So, okay, three squares thing, you please check that it is not possible. Three squares cannot add up to 2023. Okay, please think about it. It is not at all difficult. Try it. Okay, so you know that it should be either four square, five square, and you don't have to worry which one. Okay, because you know that there is a set like this possible, which is told to you. You don't even have to construct such a set. You don't even know if such a set exists actually. Right? It's a it's this. I don't know if it's easy or not. Okay, to construct such a set where you have on exactly this many ordered pairs. Yeah, that's what I was thinking first, but I had few guesses, but they were wrong. Yeah. Okay, so this is a solution. It's not difficult. This I just want to do one more question maybe. Okay, then we can go into the equivalence relation business, and then I will go over that maybe with equivalence relations and functions. And yeah, they are very, I mean, they are the they are what higher mathematics is all about in one. Yeah, that's what we are trying to do. Anyways, let's not get into all that. To put the correct kind of equivalence relation is really what higher mathematics is about. Let's try problem number 2. I see that the official solution, you can see they also have a graph theory kind of solution. Okay, but it is actually the same thing. Okay, it's just, but I'm not, otherwise I have to introduce more terms. Clicks and all, I don't think I have discussed. So yeah, the other solution is very similar to this, but this is a solution which kind of I come up with naturally. Okay, yeah, like I didn't maybe work out all the details, but it gets worked out once you know that it's equivalence relation that you should be looking for. Okay, problem 2 I am kind of not seeing, so let's try this. It's polynomials. So the coefficients are real, positive real actually. It's very strange. Show that it is impossible that each of these 101 polynomial has all roots real. Okay. Hmm. So you see, with this kind of thing, the first, yeah. So basically, what you are given is um, some positive real numbers. You can start like that. You're given some positive real numbers, and basically, you want to make polynomials out of this. Obviously, you can make a lot of polynomials out of this, but in a cyclic way, you want to. Ouch. Yeah, sorry. So yeah, in a cyclic way, you want to make a polynomial. You want to make polynomials. So like, what's the natural polynomial that you can make? Something like this, maybe. So this is the first one. No. But then they have this 100 there. So maybe you have to put that as well. This is one polynomial that you make, and then how do I say this? This is saying that you cyclically just roll the vertices, roll the coefficients, right? So this is one, and then the next one that you will make is like this. Okay, and then you keep doing that. Okay, I would say that is correct. So for example, here when the k is um, hmm, so how do you get 99? So 100 plus k is congruent to 99. K plus 1 is 0. Yeah, so when you take k equal to 100, then you get this, right? So that's correct. And then you see you keep doing this. Okay? Keep cyclically permuting. Then in general, what you are doing is you are adding k, taking it modulo 100. In general, this is what will be. Otherwise, you have to write all the 100 things if you want to see them at once. It's just k. Yeah. Hmm. And the indices are taken modulo 100. That's understood. 101. Yeah. Yes. Okay. Now show that it is impossible that each of these 101 polynomials have all roots real. So these are the kind of questions, how questions get harder. You want to prove more general things. No specific polynomial is given. It's not about any polynomial even, it's about a family of polynomials. Yeah. Yeah. So we know the question. Let's think about it. So is the question, you understand the question? Yeah. So we are saying that no matter which 101 numbers you take, no matter what 101 numbers you take, you call them A0, A1, A100. Okay. When you arrange them, when you make a polynomial out of it like this, where you just, the only thing we are doing is, this will play a role, putting 100 here. Okay. Other than that, it's just taking a polynomial with, 99 positive real coefficients. Okay. Okay. And then you have this, and it doesn't have any real roots. Okay. But even if you permute the vertices cyclically, sorry, I mean, if you permute the coefficients cyclically, right? Which is like you make a polynomial like this, and you again, you know, roll the vertices, these coefficients once again, and so on. None of the polynomials will have all roots real. They may have some real roots, but you will not get that any polynomial has all roots real. So every polynomial will have at least one non-real root. Okay, so I'll tell you again because I didn't say it properly last time. We're just saying that you start with any 100 positive numbers. You start with any 100 positive numbers. And then you take this polynomial, for example. Okay, can this polynomial have all its roots real? First tell me that. Mm, no, that is possible. Just think. That is possible. Yeah, because I understand because I gave you a wrong impression. But that is possible. So even if all the coefficients are positive, it is still possible that it has all its roots real. You can think of it, right? That's easy. Yeah. For example, what would be an example? Like x square minus 10x plus 10x no, plus 7x plus 5, right? Something like that. Right? Yeah, yeah. This has all roots real, right? But then we are saying that okay, so you may take 100 numbers and you may get all roots are real. But they are saying that now uh, cyclically shift the vertices. Cyclically shifting means like this. Okay? The last one comes. Okay? And you do that again and again. You get how many different polynomials do you get? 101 polynomials, right? They are saying that at least one of these polynomials will be such that not all of its roots will be real. At least one polynomial is there such that not all of its roots is real. Okay, so at least one polynomial has a non-real root. Now is it clear? For example, in this case, yeah, if you shift, you get this. Does this one have all its roots real? Even though the 100 is not here, but still. Does this one have all its roots real? No, right? Yeah, it already loses, right? It's 28. So this is not doesn't have it. That's what they are saying, that if you shift the coefficients, then there will come a time when the roots will not be real. At least some root will not be real. Okay, and you can kind of feel it. It's because sort of like when the largest coefficient comes here or something, right? When there is a disbalance between the sum and the product, something like that, right? Those balances which are present when everything is real is broken. So some non-real root will come. So we're just saying that there is some polynomial with some non-real root. Okay, this is a nice question. This is, yeah, I don't know. I have no idea. Okay, I have some idea. Let's think. So we have to, maybe you can assume that all the polynomials have all roots real. That's what you can assume and move forward and get a contradiction. Yeah, no, don't know actually. So it's like if I add all the polynomials, so is it true that if Px has all real roots, not true, I think. If Px and Qx have all roots real, yeah, then so does Px plus Qx. This is not true, right? Uh, or is it true? No, this should not be true. Yeah, this is not true. For example, you can take x cube and x, right? So x cube has all roots real and x has all roots real. But x cube plus x doesn't have all roots real, right? Otherwise, they would have sort of added these polynomials maybe, and because that way you get symmetry, right? The coefficients become all these terms. This summation a naught up to 800 comes in all the coefficients, which you can take common. Can we show that px plus qx has at least one real root? Can you prove this? If px and qx have all real roots, then the summation has at least one real root. Then also we could use it. Just think about that. I would want to prove it if I knew it is true. Otherwise, it seems too much work. Uh, okay, then let's break this into two parts. So, what about this? Any update on this? Is this correct? Let's try it this first. So, Px and Qx have all real roots. Okay. Then what can you say about Px plus Qx? Okay, can we say it has at least one real root? So maybe look at the root of Px, and so obviously like they don't have any common roots, right? If they had common roots, then it would come in Px plus Qx. Any doubt, right? That's clear. So let us say that alpha is a root of Px. So P is positive at alpha. No, alpha is a root of Px. So P is, like this. And then let's say it goes up after that. Uh, yeah. Now let us take some cases. Okay, let's say that the next root is maybe alpha 1 and alpha 2. Let's say the next root of Px is also this. Hmm. Hmm. I don't know this. Then in between that, let's say so in this picture, in between that, Px will be positive. It may happen that Qx is also positive. But then can we do some, so if Qx is also positive in that, so let's say this graph of Qx is above like that, then like if it's C times, if it's a constant times Px, if Qx is a constant times Px, then obviously this is true. Then Px plus Qx will just be constant times Px. Hmm. So then here Px plus Qx is positive, and here Px plus Qx becomes, so just at this point, right? Px plus Qx becomes negative, and which means that Px plus Qx will be zero at somewhere in between, right? Uh, yeah, so the way to reason this would be, mhm, that's a good question. No, they don't have to meet. Yeah, that maybe that's the case we should look at. They don't have to meet. For example, very simple example will be like this. You take x square minus 1, and then you take, yeah, take x to the power 4. Yes, they will not meet. or do they meet? They will not meet, right? So at 1 it is 0, and at 1 this is 1, right? And then certainly after that it's bigger, so it's always bigger. Yeah. Yes, and you are right. I think in this kind of situation, yeah. But then in this kind of situation, uh, uh, yeah, right. In this kind of situation, there are no roots, right, for px plus qx. Yeah. Mm, yeah, exactly. That's a counterexample. Yeah, is it okay? Or this is not a counterexample? No, this cannot be. I'm seeing something wrong. Yes. Hello. 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 Okay. No. So wait. I'm saying something wrong because this must have real roots. Then what is the problem? Yeah, it's zero. No, no, no. It has have. They don't meet, but it has real roots, of course. Yeah, and the very simple reasons are there. Because at 0 it is negative. Yeah, at 0, the summation is negative, and at some large number, the summation is positive. Uh, yeah, it is a sum, right? The sum, obviously. Yeah. Mm, yeah, but then by the same this thing, one can take this, right? Both have real roots, but the sum doesn't have real roots. And then I can take the difference, basically. No, no, so that's not correct. This doesn't have real roots. Yeah, just flip it and yeah. So then I don't know. Then I'm not willing to try that thing. Mm, yeah, this lemma is not correct. Okay, so we will move forward. Let's see. So yes, I mean, one, as I'm saying, right, because you don't really know like which polynomial is going to have the non-real root and so on. Uh, one way to go about it is by contradiction, and by reading the first line of this, so they have the solution here. Yeah, I should be doing that, going by contradiction. This lemma doesn't work, so the things I was building, trying to build on that will not work. Yeah, you can notice that all the roots are going to be negative, right? So obviously we'll say assume that all the roots are real. Assume all roots of all the polynomials are real. Yeah, maybe something like that. This 100 has to come in. So let's see. So I mean, at least so we know that the roots are negative. Okay. So maybe we will just label the roots. Okay. So like for the first polynomial, so we have p1, p2, and in this way we'll go. Okay. So or maybe not p1, maybe uh, how should I say? Maybe p0. P0, we'll call this p100. Okay, like p0, p1, p100, like that. So let us say that the roots of p0 are all real, and they are negative. So I'm following the notation on the solution to say that, let's say that they are um, uh, yeah, like this. No, that's not what I want to do. Okay, so you can understand what I'm doing. I'm writing the roots down in a nice way. Uh, yeah, the roots will become 101 for the 0th polynomial, and similarly it will go on. All the roots are negative, but then what do you do with that? Yeah, because the coefficients are positive, right? So yeah, the coefficients are positive, right? Where indices, not understanding the solution correctly or what? What roots really? No, 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 this is fine. Yeah, then some jugglery with the coefficients has to be done. Not quite sure what they are doing. Yeah, so if you, I mean, if you take this, then what happens is this. Yeah, you have to consider the aggregate, but maybe they're doing it in a slightly more interesting. Yeah. So what is happening? Like if you look at it, then this by this, everything is positive, right? So this thing, yeah, it's there, it's there. I'm sorry. Yeah, no, so this is it's bad. So you see, this thing is bigger than or equal to. So we will apply the AMGM inequality, right? So this is the sum of the roots. So what is the AM of the sum of the roots? Yeah, I mean sum of the negative and negative of the root. This is the AM, right? So you see, this will be the sum of the roots. This thing will be the sum of the roots. Is that correct? That's the formula, right? Sum of the roots. So we'll take negative of them because yeah. Then this is the negative of the sum of the roots, and then the AM will be this. Yeah, the arithmetic mean. So that was the clue which I missed. Okay, and then the geometric mean is this. So in our case, it will be just 100, right? Because 100, no, yeah, yeah, that's correct, right? That's the geometric mean, right? It's that is what it is, right? So that's correct. Okay, so basically, you see now this thing obviously you need to do for every pair of terms, right? Yes or no? Right. You need to do this for not every pair, but like every, yeah. So you'll be doing it like this. For example, the next one you'll be getting for the next polynomial. If you apply ANGM, then you'll be getting something like this, right? For the next polynomial, if you apply the same thing. Yeah, Ishana, is that correct? Hmm. So AMGM inequality, right? So you apply the AMGM inequality on these numbers. I mean, not on these numbers, on the positive of these numbers, right? So what's the AM of these numbers? It is this. Do you agree with that? Right? Some of the roots and then 100 goes out. And then this is the GM because the product of the roots is this. There the sign actually doesn't matter, even number of roots. And so the GM is that. And so AM bigger than GM. And so you have to do this for, obviously, I was adding the coefficient, which is a very naive thing. You don't have to, you should not do that, will not work. But some other way to get the contradiction. The contradiction, you don't know how it can come, kind of. You should know, one should have the some sense, which we did not have. Now maybe we have, looking at a bit of the solution. Is that you should do this for every. So if you do the same, so if you do the same thing for P100, then do you see that you will get this second inequality, right? Just the same thing. Yeah, it's just bookkeeping. 100 gets replaced by 99, 99 gets replaced by 98. Now, if you keep doing this, then finally what you will get, do this for all the polynomials and multiply them. If you multiply them, you will get 1 equal to 1. Because it's correct, right? Because see, because if you look at the left-hand sides of all of them, right, you can see that everything appears. Like so, every coefficient AI appears once in numerator and once in denominator. That's clear, right? And so the it will be 1, the product will be 1. Similarly on the left hand side, for this very simple reason that everything appears in the numerator once and in the denominator once, right? Because everything is the last coefficient once and first coefficient once. So all those reasons will tell you. So the point is that in the end you get 1 equal to 1, which means that each of these must be equality, right? There cannot be any loss at any stage, right? So all these must be equal. Is that correct? Is my conclusion correct? Yeah. And that, what does that mean? So if the first one is equality, then what does that mean? Yeah. So it means that the AM of these numbers is equal to the GM. That happens when the numbers are equal, and it never happens in any other case. Right? This is what we are getting. And this means that all the numbers are equal. Right? So what do we finally conclude? We conclude that all the roots are equal. Okay. And from there you can get a easy contradiction. So our final conclusion is that all the roots are equal for every polynomial. So all roots of P naught are equal. All roots of P1 are equal. What does this mean? This means that P naught is like, it is something like this. Maybe x plus 1 to the power 100. It is x minus alpha to the power 100, right? But what can that alpha be? You can decide for yourself, right? It has to be 1. Binomial expansion, whatever you want to think. But then you see that it is not possible for P1 to be anything else. It has to be x plus 1 to the power 100, but then its coefficients are not in that way. Or some, you can just work it out. Then then you basically know all the coefficients once you get P naught. And then you know that shifting them doesn't give you P naught. Okay. So that part, just work out that part. That is simple. All the roots are equal. That's the key thing. So it was taking the aggregate, it was taking all of them at once, which is where I was, but then I missed that thing. So my interpretation of that 100 was a little wrong. I was kind of thinking in a more analytic way that somehow, but yeah, this is Olympiad, so they will not usually, yeah, it was more discrete. Okay, that you just take AMGMs, just take AM, apply AMGM to every inequality. I mean, just basically the simplest thing, right? That you take AMGM. This is what we actually have done many times. I've done in my studies. Yeah, and once you take AMGMs like this, you will obviously have to multiply them. Right? There's not much think of the way they are arranged. Right? They cancel out. So it was, yeah. This question I don't know. First question was nice. This is also nice. Okay. So yeah, I think now we'll stop. We did two questions. Uh, but you please have to work out the details. Okay, can you do that? You should do that, otherwise you will not grow, right? Work out the details and you see, and please read up. So Ishana, officially in your syllabus you have not done binary relations and so on till now. Cartesian product of sets, not yet. Yeah, so you have to read this before the next class. Okay, try to find the time and see if you can read this, because if you do that then I can go a little faster, because I want to just explain this topic, the more finer aspects of it. So see if you can find the time. This is there, NCRT class 11, definitely. Okay. So yeah, they will do it in a very simple way to begin with, so you know. And Nagesh, I will expect that you already know it. If you don't know it, then you should also look at it. Okay. Cartesian products you will know, I suppose, but just binary relations and more on equivalence relations and so on. Then I'll say a few things. Okay, and yeah, can say some interesting things there. Okay. Yeah. So we will stop here today. Uh, yeah, what can I say? I can say that for Sunday, let us continue to solve this. Okay, let's you try the next problem 3, problem 4, maybe. Okay, look at the solutions if you want little bit. Okay, don't mind doing that. Okay, do that little bit and see if it helps you. Like, so if you just Google, you will find the solutions. Number one, there's official solution. Okay, INMO official solutions are there. So obviously it may not be easy to follow them completely. So see, try to read a little bit of them, try to see how much you can grow on that. And then on Sunday we'll try to do at least 2 or 3, maybe 3 questions. Okay, because let's finish the paper at least. Okay, let's see where we are standing. Yeah, you have to put in more and more work. So read the Cartesian product and try the problems and take help of the solutions if needed. But more than these is that work out the details of today. Work out the details of today's class. Okay. All right, then we'll meet on Sunday. Sunday is yes, and I wanted to say a few things. So yeah, Sunday 9 p.m. we will meet. Okay. And no, I will say the other things later. Any questions? No. Tomorrow we have the matrix class. Oh, yes, yes, yes. I have to take the matrix class also. Yes, but I don't think I'll be able to uh, take that one tomorrow. That is a problem. Yes, yes, yes. So I am. Oh, so for this ISI CMI entrance, and like the more like this class is okay. We are not so much. We cannot go so much advanced. But Nagesh, for you, I don't know if this time suits you. Okay, you have a look at it. So here we are having a more advanced class. But yeah, is does this time suit you on weekend? Not Sunday this week because I have something. We meet at this time. So currently we are doing probability here. We have started. Okay. So this will be Saturday. Okay. Yeah. Matrix thing again because tomorrow evening I cannot do because Sunday morning I have something which needs me to start preparing from Saturday only, evening only. We're resting and so on. So if you yeah, every Saturday and Sunday we meet, and this class we go much more faster. Okay, and we cover the other topics like expectations, probabilistic method, probability, problem not so much, but expectation, which we don't do in this class. Okay, so yeah, it maybe is it a bit early for you? Yeah. Huh. Yeah, so you can just wake up and attend the class. I think it